Okay, so now we're talking about differentials. Okay, differentials. Okay, when we initially said that dy dx is basically f dot prime, right? F prime here. So I always said that this is not dy divided by dx. This is dy dx, right? Just the differentiation of y with respect to x. Okay. Now in differentials, okay, it's a different thing. Okay. If you look at the definition there on page 241, differentials. Let y equals f of x be a differentiable function, then the differential dx is an independent variable. The differential dy is this. So now we're going to actually split this up. And we're going to say that dy is equal to f prime of dx. In other words, an easier way to think of this is the differential of y is this times the differential of x. So as x changes this amount, y will change this amount. Okay. So if you look at it that way, it becomes a little easier. So I prefer to write the differentials in this form rather than dy dx and try to figure out, well, is it a differential or not? Well, actually, when you see dy by itself, it really means it's differential, right? Because it's not dy dx, it's just dy. So it's the amount that that y changed, and this is the amount that x changed, okay? So I prefer to write it as delta y and delta x, okay? Okay, let's see if we can actually do this and see what it actually means, okay? So example number 5, this is where we have different differentials. We have example number 5. Example number 5, it says, find the differential dy and evaluate dy for the given values of x and dx. So y is equal to x to the 5th plus 37x, and I want to evaluate this when x is equal to 1 and dx is equal to 0.01. Okay, so let's go ahead and dy is going to be equal to f prime of this, right? So it's prime, so it's going to be this times a differential, right? So when x is equal to 1, I'm going to put that in here. So I'm going to get 5 plus that, so it'll be 42 times the dx is equal to 0.01. So it's going to be 0.42. Okay, so that's that. Where am I at? Okay, A. Let's go B. In B, we have y is equal to sine of 3x. And x is equal to pi. And dx is equal to negative 0.02. So I get f prime of x is going to be equal to the differentiation of this. So it's going to be cosine 3x, but then I have to do the chain rule. So I have to take the derivative of 3x. So 3 appears here. So f prime of pi is equal to 3 times cosine 3 pi. Cosine 3 pi is equal to what? Eva.
-1.
Yes, because cosine of 3 pi is the same as cosine pi, correct? The same with cosine pi. Cosine pi is -1. So -3, right? -3. So dy, the differential of y is what we're trying to find here, is going to be equal to -3 times dx, 0.02, -0.06. Okay, in other words, when x changes in the -2, when it goes down 0.02, the y is going to change in this manner. Okay, all right, so What am I missing? Oh, it's negative 0.02. I'm sorry. Negative 0.02. So it's positive 0.06. Okay. So that was B. Let's go ahead and do C. X plus y is equal to xy. And I want to find out this one is equal to 2 and dx is equal to 0.05. So what do we have here? We have y, but y is given to us not explicitly. It is given to us in an implicit function. So we have to find the implicit differentiation here, right? So I take the derivative of this, so I get 1 plus y prime is equal to the product rule. Take the derivative of that, I get 1 times y plus x times y prime. So I have y prime, let's collect the y primes. I'm going to get 1 minus x, y prime. This one goes over here. I have y plus 1. So y prime is equal to y plus 1, 1 minus x. Okay, so I have to evaluate this. I know what the x is, but I don't know what the y is, right? So I can find what the y is by putting my x into here. So I have 2 plus y is equal to 2 times y. So it looks like y is going to be equal to 2, right? So we move this over, I get y is equal to 2. So I'm going to evaluate this at when x is equal to 2 and y is equal to 2. So I put that in there, I get, this is minus 1, because the 1 went over here, y minus 1. So this is minus 1, 2 minus 1 over 1 minus 2, 1 over negative 1, so it's going to be negative 1. Okay? So y is equal to negative 1, so I get dy is equal to negative 1 times dx 0.05, negative 0.05 is going to be the answer. Okay? Everybody good there? He gave us kind of a curveball here by giving us into the implicit way, right? Implicit function. And I also had to find out what y was when x equals to 2, right? Okay, so that's that. Flip the page. Let's do example number 6. Example number 6. Find the differentials of the function. So d of tan 2x. So if I take the derivative of, do I need to do this? So if I take the derivative of this, what do I get? I get secant squared 2x. Then I also have to do the chain rule. So I take the derivative of 2x, so the 2 shows up there. Okay, so that is going to be equal to that. And the next one is dx over x plus 1. So what am I going to use here? I'm going to do the quotient rule, right? Low d high minus high d low. I can take the derivative of the low, which is 1, which is going to be x plus 1 minus x, so the x's cancel out. And I'm going to get x plus 1 squared. There you go. Okay, so there's a green box on the 242. It says differential estimate of change. The differential df is equal to f prime x dx has a geometric interpretation. If we think of dx as delta x, that's like I was saying earlier, the change in x, then the value of df at x equals a is delta L, the change in the linear approximation of f. If f is differentiable at x equals a, then the approximate change in f when x changes from a to a plus dx can be represented as this right here. Okay, sensitivity, definition. Sensitivity is an interpretation of the derivative describing how small changes in the input variable, delta x, right, produces changes in the output variable. For smaller values of delta x, we can approximate delta y by saying that. Okay, all right. So let's go ahead and see, let's go ahead and actually just go ahead and do the examples and see what this actually means. Let's go example number 7 and see what we can do here. I think when we do example 7, some of this might be become a little more clear what they're actually talking about. Example number 7, the radius r of a circle increases from 10 to 10.1. Use the linearization to estimate the increase in the circle's area and compare this estimate to the true change. Okay. Let's do the true change first. What's the true change? Because the area of a circle is pi r squared. So the true change is 10.1 squared minus 10 squared, correct? Because this is the original. This is the new one. We're just finding the difference, right? If you do this, you're going to get what? The book said if I do this, I get 2.01 pi. Okay? Let's see if we can estimate the change. Let's see if we using the linearization, let's go and estimate the change. So I get what? A prime is going to be equal to 2 pi r when it's equal to 10, right? Because I'm going to get 10, and what do I get here? I get 100 pi, right? Because when r is equal to 10, my value is 100 pi. So the linear approximation of 10.1 is going to be equal to 10. So it's going to be 100 pi, right? 100 pi plus this guy evaluated at 10th, a new one, right? So it's going to be, no, it's going to be 20 pi, I'm sorry, 20 pi times the delta, which is 0.1. 1, right? Delta there, so if I do that, this is going to be 2 pi, so I'm going to get 102 pi. Okay, so if by approximating, this is what we approximated, okay? So if I find the change using the approximation, I'm going to get this 102 pi minus 100 pi, right? Because 100 pi was what I started with, right? 100 pi is what I started with right here. So 102 minus 100 pi is going to be equal to 2 pi. So when I use the approximation, I find that the delta y is going to be equal to 2 pi, whereas the true is 2.01 pi. Again, you can see that this is very, very close. Okay? So let's go ahead and look at the next one. It says absolute, relative, and percentage change.
Mr. On?
Yes.
Now he's in the waiting room.
No. Where has she been all this time?
She said her internet was down.
Oh, I heard that one before. Okay. We understand what we're doing here, right? So the percentage change here would be what? the percentage change would be, I started with 100 pi, and this is what I got, the 2 pi, right? So percentage change would be 2%, right? And then there's the relative change and the absolute change, okay? I'm gonna let you guys go ahead and read that because this is really, again, this is stuff you did in algebra and pre-algebra, right? The relative, absolute, right? All that kind of stuff. So let's go ahead and flip the page. And so there are, let's do one of these just to make sure that we get it. Let's do example number 10. See if we can do that together and see how this works out. Example number 10, about how accurately should we measure the radius r of a sphere to calculate the surface area of that within 1% of its true value, okay? Right, so the question is that I want to have, right? So what is my S prime is going to be equal to 8 pi r, right? And I want a, what did I want? I want a 1% within 1% of its true value, right? So let's go ahead and find, so my delta S that I would find at that point is going to be equal to 8 pi r times delta r, right? And I want that, this guy here, to be less than 1%, right? So what do I get here? I'm going to get, am I going too fast here? So delta S is going to be equal to what? Delta S, so I want delta S to be less than 0.01 of S, of the true S, right? The true S will be 4 pi, so I get 0.01 times pi r squared. And that's what I'm trying to do, right? So if I do that, what do I get? Right, this guy here is going to be equal to that guy. So I want this to be less than that. So I want 8 pi r delta r to be less than 4 pi r squared over 100. Pi's cancel out, 4 cancel out to 2, move the 200 over. I get 200 r delta r squared, r's cancel out. So I'm going to get delta r has to be less than that. So I cannot change the r greater than 1/200th of the original radius, because if I do more than that, I will get this will not work. So I'll have a greater than 1% difference there, okay? Okay, so Newton's method. Let's go ahead and quickly go over Newton's method. Newton's method is fairly involved. So I'm going to do the truncated or the Reader's Digest version here. Okay. Newton came up with a way to find, if I have what we're trying to find is we're trying to find the true root here. We're trying to find the true root. Okay. Newton found that if I start with a guess here, if I guess this, right, and I found that was not good. If I found the tangent line here, okay, at that point, okay, again, if I found out where that met at the x here, because I can find this, right? If this is x, oh, we'll call this x1, okay? This is f of x1. Okay, if I found the tangent line function here is going to be what? The function is going to be y, the line is going to be y minus this guy, f of x1 is equal to f prime at x1, x minus x1, correct? Over the point slope equation, okay? So if I go ahead and set the y equal to 0 here, I can find this guy, which we'll call x2, right? And if I do that one more time, and then find that, and then get closer and closer, I can get closer and closer. So every time I do this, so basically what he's saying that within 2 to 3 of these guesses, I should be able to find the true or something very close to the true root here, okay? The problem with this method is that it sometimes does not work. In other words, you can see how I do this, if I do this, and I do it one more time, it converges onto the true root. Sometimes it does not converge, okay? So let's go ahead and look at the bottom of page 245, and it goes over the procedure for the Newton's method, okay? Guess a first approximation to a solution to the equation, and then use the first approximation to get a second, the second to get a third, and so on. So you're basically doing this, 2 or 3 times until you come to a number, converge on to a number, and we're going to call that the answer. So let's look at example number 13. Okay? I'm not going to go through it, but let's read through it. So use the Newton's method to solve x cubed plus 3x plus 1 is equal to 0. Okay? So you're going to find the f prime, and you're going to find the first guess. So in this one, they're going to guess, their guess is going to be negative 0.03. So negative 0.03, you guess that, and you put that in there, and you're going to find x1, a value for x1, x2. So you guessed the first one. The guess was 0.03, negative 0.03, so that's x1. x2 is when you go ahead and put all the numbers in, you get negative 0.322324. And you can see it quickly converges after like the third one. You can say it's pretty close to negative 0.322. And you can call it good, really, at that point. So again, 2 or 3 times, and it should converge to something. The problem is, underneath there, it says, Newton's method may fail. So sometimes there are certain times when this procedure does not work. Okay, instead of converging, it just goes back and forth, and it doesn't work. Okay, and it kind of diagrams that why it could fail. Okay, so just know that there is a way to do it, and the way you do it is you find the tangent line equation at that point. You find out where that meets 0, and that's your second guess. And then you're going to put that guy in and to find the tangent line for x2, and then you're going to find the tangent line equation again, and then find out where it hits 0 again at the x-axis. And you do that 2 or 3 times, and you should be able to find the root. Okay? And that is Newton's method. All right? So we're going to call that good.